Let's take a look at Kepler's laws for the orbits of planets around the Sun. And we have Saturn going around the Sun here. And of course, it's probably several years by Earth standards, but it's doing its one orbit. And we're going to call that orbit time period T. And the first law says there will be an elliptical orbit with the Sun at one focal point and empty space at the other. And this is something we know. Planets do not go around the Sun, okay, completely symmetrical. They do have an ellipse to them. But when we calculate the radius r, we're going to base that on an average distance to the Sun. And that average is based on the semi-major axis and the semi-minor axis of the elliptical orbit. The second law is that a line drawn from the Sun to any planet sweeps out equal areas and equal time intervals. We'll see what that looks like in a minute. But essentially means if the planet moves from this point to about right there, it's going to move from here to there in equal times. And finally, the square of the orbital period is proportional to the cube of the average distance from the planet to the Sun. Okay, let's apply the last two laws in an example here. Let's say we have the Earth going around the Sun, and at any moment it's located here, and at time t later it's located here. So we'll call that time t. Now let's take that same time interval and apply it closer to the Sun. Let's say we're located here, and then at the same time t we're now located here at a different distance. So let's draw lines, okay, from the center of the Sun out to the orbit of the planet. Draw right there, and draw right there. Likewise, from the center, from here and to here. Now remember, the time it took the Earth to go from here to there is the same time when it's closer. We're going from here to there in the same time. Let's shade that area then. Okay, so I'm going to shade this area. So the area bound by the curve, try to briefly sketch this out for you. This whole area must equal this whole area here. Now if this is true, the linear velocity at both locations can't be the same. So let's call this one v1 and this v2 here. Because the Earth moves from here to there in the same time as it goes around here, mapping out equal areas again, that piece of area here must equal this here, then the velocities can't be the same. So v2 must then be greater than v1, because the same time interval occurs from here to there as it does around here. And that's how the Kepler's second law works. Now let's find out, okay, how we can do the Kepler's third law. The way we do that is we pretend that the orbits are circular. We know that they're not. But just remind ourselves, if I go once around a circle, linear velocity does equal 2 pi r divided by time. Now again, we're in an ellipse here, so the r is going to be an average radius, and it's based on the semi-major and semi-minor axis. Okay, we know that force of gravity is what keeps the planets going around the Sun. So we're going to say force gravity must equal force centripetal, because again, it's an orbit that's in a circular pattern, even though it is an ellipse. Okay, this is something we've already derived before. We call this little m, and the star is a capital M. We'll have g, capital M, little m, divided by r squared equals little m v squared divided by r. Now little m's cross off, and one of the radius values do cross off. Okay, and we're left with an equation that is g big M divided by r is equal to v squared. Okay, so I'm going to write that over here. G big M little r is equal to, now I'm going to put in 2 pi r divided by time for my v squared. So that's 2 pi r divided by time, and I'm going to square that. Okay, then I'm going to, crisscross, because this is a proportion. And then I'm going to solve for t squared. I'll let you do the algebra, but you can quite quickly verify that this is true. So t squared is going to equal then 4 pi squared r cubed divided by gm. So let's look at the equation here. So indeed, the orbital period squared is proportional to r cubed. 4 pi squared gm, these are all going to be constants. And m stands for the mass of the star, or whatever is being have something revolving around it. It's always the central object. Now we're in a plug and chug equation. We can plug in for the r about 1.5 times 10 to the 11th for r cubed, and the time is roughly 3.2 times 10 to the 7th. And we cube that. We will be solving for m, the mass of the sun, and the mass, if you were to plug those in, is 1.991 times 10 to the 30th kilograms, which is about 1 million times more massive than our sun, or rather than our Earth.